Hello. Well, this is the second most fun part of this course, the first being multi-threading and synchronization, which is coming up very soon. Please look forward to it. I just have a quick demo before the lab. So let's have a function called foo, and it takes in an int x and an int y, and it has a local variable that's an int pointer p, and it equals malloc. We'll allocate 42 bytes, whatever. Okay, and int main, and we'll just call foo with parameters 1 and 2. Okay, so just as a sanity check, what's wrong with this function? It's a memory leak. Okay, and let's just so gcc stack is example.c, and we'll run this through valgrind. A.out. Okay, so it sees that. So we see that we have 42 bytes lost. So let's try and free this in a very strange way. So we have void bar, and then we'll have int a, int b. So it takes the same number of parameters, and we just declare an int pointer k, and we don't initialize it, and then we call free k. So what in the world are we freeing here, right? So we call bar with 3 and 4, whatever. So we'll compile this, and I'm off screen. So we'll compile this, and then we'll run valgrind, and it says all heap blocks are freed. Right. I hope this is a little bit strange, and hopefully from our understanding of how the stack looks, we can reason through what is going on here. Okay, drawing this out might give you a little better idea of what's going on. So let's say at the beginning, so we're in main, and let's say R5 is pointing down here, and we will make space for the arguments to foo. Okay, so this will be the caller prologue log, okay, and we put so we decrement the stack pointer, and now it will point up here. So we're making 8 bytes since we need 2 4-byte variables, and we put 1 and 2 over here, right? And now we are in foo, and let's just say pointers are 4 bytes just to make this drawing a little bit better. And this is the callee prologue. We decrement the stack pointer by another 8, and the return address goes right here, and our int pointer p will go right here. And we call malloc. So malloc, it probably, it's another function call, so it probably allocates more stack space, but let's just ignore that part, because so this would now point to some place on the heap. And let's say this is at OX 3000. So now P will have the value OX 3000. Okay. And now foo finishes, so it will pop the return address off the stack, and it'll return, right? So this is the callee epilogue, and we increment the stack pointer to deallocate the stack, and this is deallocated. So notice that when we deallocate, all we're doing is decrementing or incrementing the stack pointer. Just for performance, we don't bother clearing memory, right? Just because when we do a lot of function calls, it is not performant to do so. Okay. And now we are back in main, and we have to deallocate the space for the arguments as well. So now stack pointer is pointing down here. So we just incremented it by another 8. And this is the caller epilogue. And this gets allocated. Okay. So now when we call bar with 3 and 4, it's basically the same thing again. So we decrement the stack pointer. So now it points up here, and our arguments are 3 and 4. Right? And then when we are in bar, we decrement the stack pointer again to make space for the local variable as well as the return address. And now we will call free. So k would be sitting right here. So k will have the value of k was the value of p because we did not clear memory. So when we call free, it will go and free this spot. All right. True or false? So if you don't remember the answers to these, it is probably pretty good to decide in your mind the answers to these before you wait for me to explain it. Right? Something active learning. You've heard that before. All right. So true or false? A procedure's return address is computed at the beginning of that procedure, i.e. in the callee's prologue. So true or false? So we can think about a function call. So we have something like get program counter 6 R6, and then we jump to that function. Right? So when it says computed, it's talking about this this line. So it is computed at the beginning of the caller prologue. Okay. So this is false. Right. True or false? Activation frames are dynamically allocated on the stack. One way to justify this is to think of our understanding of how functions are called. You could think of a really simple recursive function that computes the sum of the elements of an array, of a dynamic array. Okay. I don't know why this needs to be recursive. I don't know, flashbacks of Racket. So the size will not be known at compile time, right? So the size will be determined at runtime, so we cannot know statically how many times this function will be called. So we don't know beforehand how high our stack is going to grow, right? Another example is from CompSci 121, when we talk about Turing machines. Remember the halting problem? So we cannot determine beforehand whether a program will either halt or continue running forever, right? So if this question was false, then this would break some fundamental theorem of computational science, right? Okay. The offset to a local variable from the beginning of its activation frame is usually statically known. So let me scroll to the previous example. So here we'll have our offsets like 0, 4, 8, 12. And this was X and Y, right? So if we wanted to get Y, it would be something like load 12 or 5 into R1, whatever. So the compiler must be able to generate this line. So it must know the offsets statically. Um, the word usually is a little bit strange here. So what does that mean? So if we have a function and it contains an array, a static array of size n. So what would the stack for this look like? So we'll have something like our return address goes here, okay, and then it actually allocates a pointer. It allocates an array pointer or an int pointer, and then this will point to the beginning of the array. So let's say that's the beginning, that's array 0, and then so on, and this will be array n-1. Okay, so yeah, it gets a bit, it gets pretty complicated, but in CS 2.13, we just learned like the basic layout of a struct of the stack, right? When you go into 3.13, it gets a lot more crazy. You'll have something called a base pointer, and have fun. So this is true. Okay, and this last one, variables are allocated. So malloc. Okay, this is on heap. Okay, like I'm like, why is this question even here? This is, yeah. So this is false. Okay. All right, reverse engineering. I've added the function bar that calls f just to make this example a little bit more interesting. So let's go through this line by line and see what it's doing. So r5 minus equals 4. And then we're saving the return address to the stack. So this one is store return address to the stack. So these two lines would be the call Lee prologue. And so a few questions now. Do we have any local variables? No, we do not. Do we have any arguments to the function foo? We also don't have any. We don't have any arguments. Okay. So here we calculate the return address. Calculate return address, and it will be saved to R6. So it's 6 bytes away from the program counter. So basically, this will be the value of R6, the address of the line that comes after the jump, right? Because after we return from F, we'll want to return to this line, the line right after. Okay, so this is the caller prologue. Okay, and then we jump to F, and when we come back, technically maybe this is not the best example, because if we had arguments, then here would be the, like right here, the non-existent lines. This would be the caller epilogue. Okay. But we don't have any arguments, so yeah. And then we retrieve the return address from the stack. So we're getting ready to return. So retrieve return address from the stack. And then this is just deallocating the stack, or deallocating the space for the return address. Minus equals 4. And then that's just return. Okay. So this is the caller epilogue. Oh god, I made a mistake up here, didn't I? No, sorry. The call Lee epilogue. Yeah. Okay. And then we go on to this next line. So now we are in the function foo, okay? Or f. And this is R5 minus equals 4. And then this is, it's saving the return address to the stack again. And then here, so this is, so this is the callee prologue. Okay. And here, we are making 12 bytes on the stack. So R5 minus equals 12. And at this point, this would be a little bit ambiguous to whether or not it's this is making space for local variables or it's making space for arguments. But we don't see any get program counter or a jump to another function. So this is not. So these would be local variables. And also at this point, we don't know if whether this is like 6 shorts or 12 characters or 4 ints. Okay, so at this point, we only know that we're making space for 12 bytes. Okay. So this whole thing is the callee prologue, okay, which is the return address as well as the local variables. Then we load 0 into R0. So R0 equals 0. Don't really know what that means yet. And then R1 equals A. Okay. And A, it looks like it's some kind of, we're loading the value of some kind of global variable. Okay. So at this point, we know that we have a global variable A. That's, A, and then we have something like F, and it takes in no arguments because it doesn't look like we use any arguments here. Well, and also in bar we didn't. So we have something that is size 12. Don't really know what that is yet. So in this next line, right here, we are using R1 as the base address of an array, and the index, it looks like it's R0. So now we know R0 equals some kind of index. Okay, so this is doing R2 equals A of I, and we'll branch to L1 if R2 is equal to 0. So go to L1 if A of I, that's an I, equals 0. Right? And then we are storing AI into R5 at index I. So what is R5? So let's just have a sketch of our stack. So return address was down here, right? And then we made 12 bytes of space. So and it looks like we are accessing some array that elements are size 4. So now we know the type of this array. And this will have 3 elements of 4 bytes each. I will call this L for local. So this is L0, L1, L2. All right. And R5 is pointing up here, and we are storing into some index of this array. So this is doing L of I equals A of I. Okay, so now we have some kind of loop that begins int I equals 0, and then it continues on as long as I is not equal to 0. because if it's equal to 0, we jump out. And then it does inc r0, so this is just doing I++, and then we branch back to the beginning of the loop. So our loop, so I++, and then we'll have L of I is equal to A of I. And this is our function. So here, so this is doing R5 minus equals 12. So this is deallocating the local variables. And then we are retrieve the return address. So R5 was pointing up here, and now R5 is pointing right here. And we retrieve it from offset 0, which was, since stack pointer is now pointing down here, we are retrieving the return address and we're putting it into R6. Then we finally deallocate the space for the return address, and then we return. Okay, so this is just deallocating space for the return address. So R5 plus equals 12. That's a plus. And then that's return. So this thing will be the call Lee eplog. Okay. All right. And yeah, so does this function return anything? So it's a little bit ambiguous to whether or not this function returns anything. Let me just rewrite it here. So it looks like we had bar, and then bar, it took in no arguments, right? Right here. And bar simply calls foo. So bar calls foo with no arguments. Okay. And foo, or f, right? And f will look like, so f has no arguments. And then we have our int. So this is our global array A. And then, so we have int L, and it's an array of size 3. Int I equals 0, I, it's not, AI is not equal to 0, I++, and then, what was it? So so it's L of I equals A of I. So yeah, so does this function return anything? So you have to be careful that what we leave in R0 is technically the return address, is technically the return value. So technically this function, it could return an int. So it could return I, because we left the final value of I inside R0, right? And R0 is the return value. So that then you would have to bring this in out of this for loop, but yeah. And technically bar could also return an int. So this just returns f. Returns the value of f, because maybe I should have even mentioned the return value, but just know that what you leave in the register 0 will be the return value. And to really know whether or not it returns anything, you have to look at like the context of how R0 is used. So we don't see what calls bar, but if something calls bar and it uses R0, then you will know that it's actually returning something useful. And yeah. So if you look at the written solutions, there's no return value. Yeah, you can, yeah, it's, yeah. What's my point? This program has a vulnerability. What is it? Well, buffer overflow. Okay, so let's think of an input for A that would cause problems. So if it's just 1 1 1 1 0. So our stack frame, it looked like this. So we have return address down here, and then we had L0, L1, and L2. Okay. So if the array was like that, then this loop continues on until it sees a 0. So it keeps writing into this local array even though it's only size 3 until it sees a 0. So this will put the 1 here, 1 here, 1 here, 1 here, and then it stops. So at the end of this the f function, we retrieve what was on a stack, and we jump to it, right? So we retrieve the return address from the stack and we jump to it. So this will jump to the address 1, and then it'll start executing whatever's at address 1. Okay. So we overwrote what we shouldn't have. So assuming you have control over the variable A, exploit this program to execute a known function. So let's turn f into a infinite recursive loop. So infinite recursive loop. So let's say we know that f is at pos 1 2 3 4, just some address. So the function f is at address 1 2 3 4. So what would the contents of our array be? So it would be array equals, so we just have some non-zero values, and then we have the address of foo 2 3 4, and then we need a 0 to make it stop. Okay. So this will put the 1 there, and then this will put ox 1 2 3 4. So this will keep jumping back to foo and just keep jumping back to foo. Okay. So we've turned this into an infinite recursive loop. So so assuming that you have control over this array, and you know the stack address, how would you exploit this program to launch a shell? I don't really. I mean, that's basically just the assignment, right? So I want to highlight the sentence or the words right here. Suppose that you know the address of the stack frame. So let's say the stack frame is at OX 3000. So it's actually very difficult to know the address of the beginning of the stack frame. As we'll see in 2F, there's a ton of modern protections to protect against this. So if you recall from lecture, the Morse worm. So how Morse was able to guess the address of the stack was probably he did a lot of trial and error, and then he was probably able to make an educated guess on where the stack frame was, because he had access to the source code as well as the he knew what architecture it would be running on, right? And I think computers were also a lot simpler back then. And we also had something called a NOP slide. So the NOP slide was to give a bigger target, so that if your virus was at the end of this NOP slide, you could you have a larger range of addresses to guess into. So you have a higher probability of hitting the NOP slide, and then it just goes down, and then so it does nothing until it hits your virus. Okay, so in this example, we know exactly where the stack frame is, and also in assignment 7, we also have access to the source code, just like Morris, right? We have access to the .s files, and we have access, like we understand the architecture of SM213. So we know where the stack is. Okay, so so the contents of this array will be, so array equals something something something, and then OX 3000, and then a 0. Okay, so this will cause it to go back. So this will cause it to return into the stack itself. Okay. So what would the values of A be? So if you could fit your shellcode within 12 bytes, then this would be the machine code of your virus. Okay. So let me show you a very simple virus. So let's say our virus was just to set the registers 1 and 2 to -1. So let's say our virus was like load -1 into R1 and load -1 into R2. So what would the machine code for this be? So if you pull up your ISA, you'll see that the machine code is like OD something, and then VVVVVVV, which is the value. So in machine code, these two lines would be 0100, and then -1 is all Fs, right? 2, 3, 4, F, 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 and same thing for other one, F, 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 F. So since our array is 4 byte values, we'll have to break this into 4 byte values. So that's the first byte, that's the second byte, and then that's the third byte, or third int, sorry. So here we'll have OX 0100 F F F F F F F F, and then here we have OX. Did I mess up? Yeah. I'm not doing another check. Let me make this a bit bigger. Okay, so this is OX 0100 F F F F. So that's 4 bytes. Yeah. OX F F F F 0200, and then OX F F F F F F F F. Right. So this will be our virus to set these two registers to 1. And oh god, it's bright. So this is test.s. So which is like 7 point something. Never mind. I don't remember. But this program, it reads in up to 128 bytes. And then it stores it somewhere, and then it jumps to that location, and it starts executing your input bytes as if it were instructions. And so in the assignment, this would be your shellcode. I'll just show you this very simple virus of setting our registers into some into -1. So it was 0 1 0 0 f f f f f f f f 0 2 0 0 f f f f f f f f. Okay, so this should set R1 and R2 to -1. There. Okay, so that's our very simple virus. Okay, yeah, have fun in the assignment. Okay, so yeah, let's talk about some modern protections. So how would you protect against this attack? So so first check bounds. I mean, come on, that's right. That's probably the simplest way to protect against this. But okay, and the other way, so another modern protection we have that you've talked about in class, something about a bird. So we have canaries. Just in case you don't remember the story from lecture, a canary was used in coal mines back in the day to detect like a leakage of methane or whatever gas, because the canary would die first before the humans, right? So what would this mean in code? So our stack before, it looked like this, right? So return address was here, and then we had our local variables, L2. So instead of this, right before the return address, we put our canary. So this would be our canary. And we just set this to some random value that the compiler knows. L0, L1, L2. So if we ended up having a buffer overflow, then it would overwrite this this value, right? So right before we return, we could check this value, or rather the compiler would check that value. So if this value is changed, that means a possible stack smash has been detected. Okay, and that's actually the error message that you do get. Okay. So another modern protection we have is something called address space layout randomization. So it basically does exactly what the name implies. It just puts your code regions at unpredictable addresses, right? So if our address space looked like this, so if I think it was like code up here, and then you had your static variables, and then you have heap that grows down, and then you have stack that grows up. So this is far too predictable, so just mess this up. Or just put the stack somewhere unpredictable. Okay. Apparently there's still ways to get around this. Brute force. Yeah. Like apparently if you have a 32-bit address space, like it doesn't take that long to brute force through a predictable range of it doesn't take long to brute force to find where the stack is. It's a bit harder on 64-bit, but I don't know. You could search this up on YouTube. That's where I briefly learned about this. Yeah, I'd recommend a channel called Live Overflow. He's super interesting. And of course, if you really like this stuff, join Robert's CTF team. Okay. And another modern protection we have is something called a non-executable stack. Okay. So this basically means just, so again, stack was down here, heap, static variables, and code. So we could make this region non-executable. So maybe it only has read and write. It only has read and write privileges. Okay. So yeah. So the problem with this is that, so like, cybersecurity is a constant cat and mouse game of the attacker being more clever, and then the defender has to be also progressively more clever, right? So yeah, again, we have the code region up here. We have heap. Sorry, this was static variables, and then we have heap. So instead of returning to the stack, so this is something called return oriented programming. So in lecture, Professor Philly I think he mentioned this briefly. So instead of returning to the stack, since it's now non-executable, we could return to the code region, right? So we could return to a function that is already in the code region, since we can't execute what's on the stack, but we could find some function that is already existing in our program and execute that instead. Okay. And I think there's probably something called return to heap as well. Like you can malloc a series of bytes that correspond to machine code for some kind of virus, right? So yeah. So specifically, if you're interested in this, you could look up something called return to libc. So what does this mean? So at the top of every program, we did something like include standard library .h, right? So this is pretty much at the top of like every C program. So that would exist in the code region, and we could return to that instead. We could return to a function that is already existing in the C standard library, hence return to libc. And what is in libc? So within libc, there's a function called execute. It's a system call, and it basically lets you execute some command. So you could make it execute /bin/sh. Yeah. So again, I recommend you look up the channel Live Overflow. And specifically, I think he has a video called Return to libc, and it does something like that. It returns to a function that is already in the C standard library, which is already in the code region of your C program. Okay. Yeah. Have fun on the assignment if you haven't finished it.